Imagine standing at the shore of an ocean you can never cross. The waves stretch endlessly before you, and on the far horizon lie islands of unimaginable beauty, worlds where water flows freely, where atmospheres shimmer with breathable air, where life might already be waiting. You can see them through your most powerful telescopes. You can measure their temperatures, analyze their chemical signatures, even estimate whether they harbor forests or oceans. But you cannot reach them, not in your lifetime, not in 1,000 lifetimes. This is humanity's condition. We are islanders trapped on a single rock, surrounded by an ocean of space so vast that it mocks every attempt to cross it. The nearest potentially habitable world sits just over 4 light-years away. Our fastest spacecraft would take 70,000 years to arrive. The journey would span the entire history of human civilization, from the Ice Age to the present, and then continue for another 60 millennia into an unknowable future. We have built rockets that can escape Earth's gravity. We have landed machines on Mars and sent probes past the edge of our solar system. We have photographed galaxies billions of light-years distant and decoded the chemical composition of alien atmospheres. Yet all of this represents exploration from behind glass, observation without presence. We remain fundamentally confined, our ambitions constrained by a law of physics so ironclad that it has defined the limits of possible motion for over a century. Nothing with mass can travel faster than light. This is not a suggestion or a guideline. It is woven into the mathematical fabric of spacetime itself. Albert Einstein proved it in equations that have withstood every experimental test we have devised. As you accelerate toward the speed of light, your mass increases. The energy required to push you faster grows exponentially until, at the threshold of light speed itself, it becomes infinite. The universe places an absolute ceiling on velocity, and that ceiling is unreachable. For generations, physicists accepted this as the final word on cosmic travel. The speed of light is the universal limit, they taught. Breaking it would be like creating a square circle or making 2 + 2 = 5, a logical impossibility embedded in reality's operating system. Textbooks declared the case closed. Popular science documentaries explained why interstellar travel would always require generation ships, suspended animation, or acceptance that voyages would outlast empires. But some scientists refused to accept permanent defeat. They began asking a different kind of question, one that would eventually crack open a doorway that everyone believed had been permanently sealed. What if we have been thinking about movement all wrong? The prison we inhabit is not constructed from steel or stone. It is built from distance itself. Space between stars is not merely empty, it is monstrously, incomprehensibly vast. Light, the fastest thing in the universe, takes years to cross the gap between neighboring solar systems. Our own galaxy measures 100,000 light-years from edge to edge. Crossing it at light speed would consume more time than human civilization has existed. Consider what this means in practical terms. The star closest to our sun, Proxima Centauri, glows just over 4 light-years away. If you could somehow travel at 99% of light speed already, an achievement beyond anything our current physics can accomplish, the journey would still consume more than 4 years of your life. Your friends and family back on Earth would age decades or centuries due to time dilation, the cruel mathematical consequence of moving at relativistic speeds. You would return to a world where everyone you knew had long since died, their descendants now elderly strangers. This temporal disconnect represents one of the universe's cruelest jokes. Even if we solve the engineering challenges of near light speed travel, even if we develop propulsion systems capable of accelerating massive spacecraft to 99% of maximum velocity, the travelers would become exiles in time itself. They would not be exploring space. They would be abandoning their entire era of history, jumping decades or centuries forward with every voyage while experiencing only months or years personally. The fastest object humanity has ever built, the Parker Solar Probe, screams through space at nearly 200,000 miles per hour. This represents an engineering triumph. A spacecraft moving so rapidly that it completes an orbit around the sun in just months. Yet even this velocity is pathetic on cosmic scales. At that speed, reaching Proxima Centauri would require 70,000 years of continuous flight. The probe would need to maintain course and function flawlessly across a time span equivalent to the entire history of anatomically modern humans, from the first cave paintings to the present day, and then continuing for another 60 millennia. We are not talking about difficult engineering problems. We are describing fundamental impossibilities. Every conventional propulsion system operates on the same basic principle. Accelerate mass by throwing other mass in the opposite direction. Chemical rockets burn fuel and expel hot gas. Ion engines shoot electrified particles. Nuclear thermal systems blast superheated propellant. All of them obey Newton's third law for every action, an equal and opposite reaction. And all of them are pitifully slow when measured against the distances that separate stars. Engineers call this the tyranny of the rocket equation. The more fuel you carry, the heavier your spacecraft becomes. The heavier your craft, the more fuel you need to accelerate it. This spiral compounds viciously. To reach even a modest fraction of light speed using chemical propulsion would require fuel tanks larger than cities, carrying masses greater than mountains, all to move a payload the size of a small car. Even exotic propulsion concepts run into immovable barriers. Nuclear fusion, the process that powers stars themselves, offers the most energy-dense fuel chemistry can provide. Yet calculations show that accelerating a decent-sized starship to just 12% of light speed using fusion would require fuel tanks the size of skyscrapers, carrying 50,000 tons of deuterium and helium-3. The ship would be almost entirely fuel, with only a tiny capsule remaining for cargo and crew. And even this massive vessel would take 2 decades to reach the outer edges of nearby star systems, arriving at destinations where the traveler's grandchildren might not live to see results. Antimatter represents the theoretical pinnacle of fuel efficiency. When matter and antimatter meet, they annihilate completely, converting 100% of their combined mass directly into energy. This is the most efficient reaction physics permits. Yet producing even tiny quantities of antimatter requires enormous particle accelerators running for years. Creating enough antimatter fuel for a single interstellar voyage would consume more energy than human civilization generates in decades. And storing it safely presents challenges that border on science fiction magnetic bottles containing substances that would explode with nuclear force if they touch normal matter. The cosmos is filled with billions of potentially habitable planets. Telescopes have identified thousands of worlds orbiting in the habitable zones of distant stars, where temperatures permit liquid water and stable atmospheres. Some are rocky like Earth. Others may harbor vast oceans beneath ice shells or feature exotic chemistries we can barely imagine. We can see them, we can measure them, we can calculate their surface conditions with remarkable precision, but we cannot reach them. Not with current technology, not with any technology foreseeable within conventional physics. Every propulsion concept that obeys Einstein's speed limit leaves us trapped in a prison of distance, able only to observe paradise from behind impenetrable barriers. This is where the story could end, with humanity forever confined to its birth world, dreaming of stars it can see but never touch. For decades, this seemed like the inevitable conclusion written into the laws of physics themselves. Then, a graduate student obsessed with science fiction decided to check whether the warp drives from his favorite television show could actually work according to real physics. Miguel Alcubierre was not trying to revolutionize cosmology. He was simply curious whether the mathematical framework of general relativity, Einstein's theory describing how mass and energy curve spacetime, would permit the kind of faster-than-light travel depicted in popular entertainment. What he discovered stunned the physics community. The equations worked. Warp drive was not just fictional fantasy, it was mathematically permissible within the known laws of physics. Alcubierre's insight relied on a crucial distinction that most people miss when thinking about Einstein's speed limit. Relativity states that nothing with mass can move through space faster than light. Fine, but Einstein never said that space itself cannot move faster than light. This seems like wordplay, a semantic trick with no real substance, but it represents the deepest kind of loophole, one hidden in plain sight within the structure of reality itself. Space is not nothing. It is an actual thing, a fabric that can bend, stretch, twist, and flow. Every massive object creates curves in this fabric, curves we experience as gravity. Black holes warp spacetime so severely that nothing can escape once you cross their event horizons. The universe itself is expanding, with distant galaxies racing away from us as space stretches between them. And here lies the critical insight. Cosmologists have known for decades that space at the edge of the observable universe is expanding faster than light. This is not speculation or theory. It is observational fact confirmed by measurements of distant galaxies. Space itself routinely exceeds the speed limit that constrains objects moving through space. If space can already break the speed limit, why not harness that property deliberately? Alcubierre's equations described a method for creating a bubble of warped spacetime around a spacecraft. Space would contract in front of the vessel and expand behind it, generating a wave that carries the bubble forward. The ship inside would remain stationary relative to the space immediately surrounding it, experiencing no acceleration forces whatsoever. Like a surfer riding a wave, the spacecraft would be carried by spacetime itself while remaining motionless within its protective bubble. The beauty of this approach is that it sidesteps Einstein's prohibition completely. The ship is not moving through space at all. Space is moving around the ship. All the nightmare consequences of near light speed, travel time, dilation, length contraction, infinite energy requirements simply vanish because the ship never actually accelerates. Physics inside the bubble operates normally. Crew members would experience time flowing at the same rate as people back on Earth. No twin paradox, no temporal exile, no isolation from your own era. When Alcubierre published his paper in 1994, it sent shockwaves through theoretical physics. For the first time, someone had described a faster-than-light travel mechanism using accepted general relativity equations without violating causality or breaking any known laws. The concept was not science fiction. It was peer-reviewed mathematics published in a legitimate physics journal, demonstrating that warp drive appeared technically legal according to everything we know about how the universe operates. Other scientists immediately began checking his calculations, looking for errors or hidden impossibilities. They found none. The mathematics held solid. Spacetime could theoretically be warped in exactly the way Alcubierre described. The method appeared possible, not merely speculative, but genuinely possible within the framework of established physics. Of course, actually building such a device presented complications that made the theory look almost trivial by comparison. The energy requirements were astronomical. Alcubierre's original calculations suggested you would need to convert the entire mass of Jupiter into exotic matter with negative energy density, a substance that probably does not exist anywhere in the universe. Critics pounced immediately. Sure, the math works, they said. The equations are valid, but demanding materials that do not exist makes the whole concept useless. You might as well design a perpetual motion machine powered by fairy dust. The physics checks out, but the ingredients are pure fantasy. For years, this seemed like the final word. Warp drive was mathematically possible, but practically impossible, an elegant curiosity destined to remain forever theoretical. Then everything changed. In 2011, physicist Harold White published new calculations showing that optimizing the shape of the warp bubble could reduce energy requirements by several orders of magnitude. Instead of needing Jupiter's mass converted to exotic matter, you might only require several hundred kilograms. Still exotic, still unavailable. But the concept had suddenly shifted from physically impossible to merely extraordinarily difficult. Then, a decade later, something even more remarkable happened. White's research team at NASA detected something extraordinary in their laboratory, a measurable warp in spacetime at the nanometer scale. They were not trying to create a warp bubble. They were investigating whether quantum vacuum forces could be useful for basic spacecraft maneuvering. During one experimental run, their sensors picked up readings that matched theoretical predictions for what a tiny warp bubble would look like. They had accidentally created the exact spacetime geometry that Alcubierre described, just at a scale millions of times smaller than needed for actual propulsion. A warp bubble microscopic but real had appeared in a laboratory on Earth. The implications detonated through the physics community. Warp drive geometry was not theoretical anymore. It could be created, measured, and studied experimentally. If you could make a nanoscale warp bubble, then scaling it up became an engineering challenge rather than a physics impossibility. Critics demanded verification. Other laboratories needed to reproduce these results before anyone could claim definitive proof. But White's team had documented everything meticulously. The data looked solid. The effect appeared when theory predicted it should and vanished when conditions changed. Exactly the kind of correlation that suggests real phenomena rather than measurement errors. NASA quietly increased funding. Other government agencies took notice. Private aerospace companies started hiring propulsion physicists to investigate warp field generation. The race was on not to build a working warp drive immediately, but to understand whether scaling up from nano to macro was achievable within foreseeable technology. The psychological barrier had shattered. Warp bubbles existed in reality, not just on paper. That changed everything. Suddenly, research teams around the world began dusting off old papers and looking for overlooked details. Maybe the answer had been hiding in plain sight all along. Maybe the universe had already provided everything necessary, waiting for humanity to figure out the combination that unlocks faster than light travel. Because here is what nobody disputes anymore. The mathematics works. The geometry is sound. Warp drive is permitted by the known laws of physics. Whether reality actually allows the technologies needed to generate these effects at useful scales remains unknown. But for the first time in human history, faster-than-light travel has graduated from fantasy to legitimate scientific pursuit. We stand at a threshold. Behind us lies a century of certainty that the stars would remain forever beyond reach. Ahead lies possibility uncertain, difficult, perhaps still impossible, but no longer obviously so. The prison bars made of physics itself might not be quite as solid as we thought. They might bend, and if they bend, everything changes. The journey continues from the moment the old certainty breaks. The idea that the cosmic speed limit is absolute, unbreakable, and final. When that certainty cracks, another, deeper question rises beneath it. One that may be even more unsettling than the problem of reaching distant stars. If the rules of movement and distance can be bent in ways once thought impossible, what else about reality might be more flexible, more strange than everyday experience suggests? Perhaps the real frontier is not only out there among the galaxies, but also in the way the mind constructs the very world it believes it sees. Everyday life teaches a simple story. There is a stable, solid world out there, filled with objects that exist whether anyone is looking or not. Tables, trees, planets, stars, all assumed to sit in a single, objective reality that just happens to be observed by conscious creatures like us. In this picture, perception is mostly passive. Eyes are like cameras, ears like microphones, skin like pressure sensors. The brain is a central processor that receives accurate information from these biological instruments and builds a faithful 3D model of the external world. This view is comforting because it is intuitive. When a hand reaches for a glass of water, the glass is exactly where it appears to be. When a road bends out of view, the car that disappeared behind the hill continues to exist, whether anyone sees it or not. When the moon rises, it is taken for granted that a real spherical object is moving through space, reflecting sunlight toward the Earth. There is no sense in day-to-day life that reality might depend on observation, or that perception might be actively constructing a world rather than simply registering it. Yet, step into the borderlands where physics, neuroscience, and philosophy meet, and this simple picture begins to wobble. The more carefully scientists study perception, the more it looks like an active process of prediction rather than a passive recording of facts. The brain does not simply receive data from the senses. It constantly guesses what is out there, using incoming signals only to correct its own expectations. In this light, perception becomes less like a window and more like a user interface. Consider how little raw information actually reaches the brain. Light hitting the retina is just a shifting pattern of intensities and wavelengths. Sound arriving at the eardrum is nothing more than variations in air pressure over time. Touch is a set of nerve impulses triggered by distortions in the skin. On their own, these signals carry no labels. There is no tree in the stream of photons, no voice in the oscillating pressure waves. The brain must infer the world that could have produced this sensory activity. This is why illusions are so revealing. A picture that seems to move, even though it is static. Lines that appear bent but are perfectly straight. Two identical colors that look different depending on their background. These failures are not random glitches. They expose the shortcuts the brain uses to make fast guesses about what is out there. The brain is not aiming for perfect accuracy. It is aiming for survival relevant usefulness. If a shortcut usually works in natural environments, the brain uses it even if it occasionally produces a dramatic illusion in an artificial setting. Some scientists and philosophers push this idea further, suggesting that what is experienced as the external world is not reality itself, but an interface tuned by evolution. A simplified, species-specific dashboard hiding the underlying complexity of the universe. In this view, colors, sounds, textures, Even the experience of a three-dimensional space filled with objects are analogous to icons on a desktop. A folder icon on a computer screen tells nothing about the actual voltages, magnetic domains, and transistor states underlying a file. The icon is not the file. It is a convenient symbol that lets a user act without being overwhelmed by microscopic detail. Applied to perception, the argument becomes radical. Perhaps space and time themselves, as experienced, are part of this interface. Perhaps what is seen as fixed objects with shapes, colors, and positions is an efficient coding of something far stranger and more abstract, something a human brain cannot grasp directly. Maybe the world out there that seems so solid and objective is more like a set of symbols projected by the nervous system, optimized for survival rather than truth. At first glance, this may sound like pure philosophy, divorced from the solid ground of physics, but the deeper physics digs into the structure of reality. The further it drifts from the naive picture presented by the senses. Quantum mechanics, the theory governing the behavior of matter and energy at the smallest scales, offers a world in which particles seem to exist as clouds of possibilities until measured, where outcomes are described by probabilities rather than certainties, and where observation appears to play a mysterious role in determining what actually happens. In the quantum world, a particle like an electron is not a tiny billiard ball following a single precise path. Instead, it is described by a wave function, a mathematical object spreading across space, encoding a spectrum of potential positions and states. When an experiment is performed to detect where the electron is, this smooth wave of possibilities collapses into one specific result: here, now. Before the measurement, the electron is not simply unknown. It is meaningfully described only as a superposition of alternatives. Classical intuition rebels against this. How can something be in multiple states at once? How can an experiment apparently choose which potential becomes actual? For decades, physicists and philosophers have argued about what quantum mechanics really means. Some interpretations claim that reality is fundamentally probabilistic, with events genuinely not determined until they occur. Others maintain that all possible outcomes happen simultaneously in an ever-branching multiverse, and the sense of a single result is just the experience of one branch. Yet, no matter which interpretation one prefers, all agree on this: the world at quantum scales does not behave like the solid, continuous, observer-independent reality presented to the senses. The interference patterns of particles passing through two slits, the entangled correlations between particles separated by large distances, the way measurement outcomes follow precise mathematical rules, yet defy classical explanation. These phenomena point toward a universe where the straightforward picture of objects in space over time is, at best, incomplete. Modern physics has taken this strangeness further with the idea that fields, not particles, are fundamental. In quantum field theory, the universe is filled with continuous fields permeating all of space. What is called a particle is a localized excitation, a disturbance in these fields, much like a ripple in a pond. The electron field, the photon field, the quark fields, all of them exist everywhere, at every point in space, all the time. Matter is not little beads moving through emptiness. It is patterns of excitation in underlying fields. Even space-time itself may not be fundamental. Some approaches to quantum gravity suggest that space and time emerge from a deeper, more abstract layer of reality networks of information, quantum entanglement patterns, or other mathematical structures that do not resemble familiar notions of geometry. In these models, the smooth fabric of space-time is like a fluid, seemingly continuous at human scales, but built from discrete microscopic constituents when examined more closely. If space-time is emergent, then the intuitive sense of here and there, of distances and durations, could be high-level features of a deeper informational order. This idea harmonizes unexpectedly with the earlier notion that perception might be an interface. Perhaps the brain constructs a spatial, temporal world as a user-friendly representation not only of its environment, but of a universe whose basic ingredients are fundamentally non-spatial and non-temporal. This is not to say that the external world is a hallucination in the trivial sense. Rocks hurt when kicked, planets follow predictable trajectories, lasers cut through steel with unambiguous precision. The interface, if that is what perception is, must be extraordinarily consistent and law-governed. But consistency does not imply transparency. A virtual reality headset can present a stable, rule-based world without revealing the circuitry and code that generate it. The tension between these perspectives has generated multiple competing views about what reality really is. On one side stand various forms of realism, the belief that there is a mind-independent world with definite properties, and that science gradually uncovers more accurate descriptions of it. In this view, electrons, stars, and galaxies exist out there, with or without observers. Quantum mechanics is then interpreted as a strange but still objective theory about how these entities behave. On the other side, stand positions that question whether this objectivist picture can be taken at face value. Some interpretations of quantum mechanics, for example, treat the wave function as a catalog of information about potential measurement outcomes rather than a physical object. Others propose that reality is fundamentally relational, that properties like position or momentum do not exist absolutely, but only in relation to specific interactions. Still, others lean toward an information-centric universe, where what truly exists is not particles or fields, but bits of information and their transformations. Looming over all of this is a possibility even more extreme, that the universe itself might be something like a simulation or an emergent computation. In such scenarios, the familiar world of objects in space appears as the large-scale behavior of underlying informational processes. Observers, including human beings, would be part of that process, localized patterns within an evolving sea of information. Space, time, matter, energy, even the laws of physics could then be seen as emergent regularities of a deeper, more abstract substrate. Regardless of which view one favors, a common thread runs through them: the realization that the straightforward, everyday sense of reality is at most a first approximation. The solid world perceived through the senses is a constructed representation, one that works extremely well for survival and engineering, but may conceal more than it reveals about the true nature of existence. If perception is an interface, and if spacetime itself might be emergent, then the distance to the nearest star is not just a number. It is a feature of a particular layer of description, arising from deeper structures that could, in principle, be manipulated. This brings the story back to faster-than-light travel in an unexpected way. The same mathematics that describes warp bubbles and space-time curvature also hints at a universe where geometry is not absolute. Distances can stretch, contract, and twist. Gravity already demonstrates that mass and energy can change the shape of space-time. Black holes show how extreme curvature traps light itself. The warp drive proposals go further, suggesting deliberate engineering of space-time geometry, not merely riding the curves that nature provides, but sculpting new ones. The very thought that space can be moved, compressed, or expanded at will forces a shift in perspective. If distance is not an unchangeable backdrop, but a dynamic field that can be shaped, then the prison of vast interstellar gaps begins to look less like an iron cage and more like a challenge in applied geometry. The question becomes less, how do we move ships quickly through fixed space? And more, how do we persuade space to carry ships where we want them to go? To even consider this seriously, one must first loosen the grip of everyday intuition. The mind is wired to think of space as an empty stage and objects as actors moving across it. But general relativity teaches a different lesson. The stage and the actors are intertwined. Mass and energy tell spacetime how to curve. Curved spacetime tells matter how to move. There is no rigid background. There is only a dynamic, interactive fabric. Seen this way, warp drive is not a magical engine bolted to the back of a ship. It is a way of riding on the fabric of the universe itself, drawing patterns of curvature that produce motion without motion. The ship inside the bubble does nothing. It remains at rest relative to its local spacetime. Yet the pattern of curvature surrounding it carries it forward. Movement without acceleration, travel without traversing. The key obstacle lies in finding the right ink to write with, that is, the right kinds of energy and matter to create the desired spacetime geometry. Alcubierre's original solution called for regions of negative energy density, something that behaves as if it has negative mass. Normal matter curves spacetime inward, creating gravitational wells that attract. Whatever drives a warp bubble must, at least in some regions, do the opposite. Curve spacetime outward, pushing instead of pulling. At first, this requirement seemed fatal. No one had ever observed negative mass. No object had ever been measured with the bizarre property of accelerating opposite to the push direction. If gravity is a curvature of spacetime created by energy and mass, and all known energy densities are positive, then where could the repulsive curvature needed for a warp bubble be found? The answer, or at least part of it, emerged from an unexpected corner of quantum theory, the so-called vacuum. For centuries, empty space was thought to be truly empty. Later, classical physics filled it with fields like the electromagnetic field. In quantum field theory, vacuum is not nothing at all. It is a restless medium, seething with fleeting virtual particles that flicker into and out of existence, borrowing energy for brief moments before annihilating back into the background. One of the most striking demonstrations of this comes from a phenomenon known as the Casimir effect. When two uncharged metal plates are placed extremely close together in a vacuum, they are mysteriously drawn toward each other, as if some invisible hand were pushing them. The force is incredibly tiny, noticeable only at separations smaller than the width of a human hair, but it is real and measurable. The best explanation involves quantum vacuum fluctuations. Only certain wavelengths of virtual particles can exist between the plates, while all wavelengths can exist outside them. This imbalance of allowed fluctuations creates higher pressure from the outside than the inside, nudging the plates together. From one perspective, the region between the plates has less vacuum energy than the surrounding space. In a relative sense, it behaves as if it has negative energy density compared with the outside. This is not the exotic matter of science fiction, but it proves that nature permits configurations where energy density can dip below the value of the ambient vacuum. If negative relative energy can exist, perhaps the universe is less hostile to warp-like geometries than previously assumed. When Harold White and his team explored how to manipulate Casimir-like effects with carefully arranged structures, they were not expecting to stumble onto warp bubble signatures. Their goal was modest: study whether tiny quantum forces could be harnessed for practical applications, such as attitude control for small spacecraft. Yet, by fine-tuning the geometry of certain components, they generated space-time distortions that matched the theoretical shape of a miniature warp bubble. In that moment, the previously sharp line between speculative geometry and physical possibility blurred. The equations describing warp fields were no longer confined to blackboards and simulations. They now had a shadow in the laboratory, small, delicate, and far from useful, but unmistakably real. The universe had whispered back, "Yes, this geometry can exist." This does not mean starships will be cruising between galaxies anytime soon. Scaling from nanometer-scale distortions to meter-scale fields around entire vessels requires technologies that do not yet exist and energies far beyond today's capabilities. It may demand new kinds of materials, new insights into quantum vacuum engineering, and sources of power closer to miniature stars than to modern reactors. But the significance of that tiny warp bubble lies not in what it can do, but in what it proves is allowed. Once a geometry is shown to be physically realizable at any scale, the question shifts from, "Is this legal in the laws of physics?" to "What would it take to make it larger, stronger, and controllable?" History is full of examples where initially tiny, fragile effects became the foundation for revolutionary technologies. The first electrical sparks in laboratory jars seemed like curiosities. The first laser beams were solutions in search of a problem. Nuclear fission was once a purely theoretical possibility buried in equations about atomic nuclei. Warp bubbles now occupy a similar conceptual space. They are no longer forbidden territory, they are difficult territory. All of this circles back to a deeper, almost philosophical realization. The universe appears increasingly like a system whose true nature hides behind layers of description and representation. Perception offers one layer, a world of colors, objects, and persistent surfaces in three-dimensional space. Classical physics adds another, deterministic trajectories and continuous fields. Quantum mechanics adds a further layer, probabilities, superpositions, and entangled information. General relativity adds curved spacetime. Emerging theories hint at even deeper layers, networks of abstract relations, quantum information, or computational structures from which spacetime and matter arise. The human mind is situated somewhere within these layers, using its evolved interface to navigate daily life. The senses tell a story in which distances are fixed, objects are solid, and movement is the only way to go from one place to another. But behind that story lies a stranger narrative in which distance is malleable, Geometry is dynamic, and the very notions of here and there may be emergent, not fundamental. If that is true, then faster-than-light travel is not just a technical challenge, it is a conceptual revolution. It requires learning to think in terms of spacetime as something that can be engineered, of vacuum as an energetic medium that can be shaped, and of reality as a layered structure where the familiar world of experience is only one of many levels. It demands new mathematics, new machines, and perhaps most of all, new intuitions. The story of how this revolution might play out is still being written. In the next stage of this journey, the focus turns from the nature of perception and the abstract geometry of spacetime to the competing interpretations of what all this means. Realism versus anti-realism, matter versus information, universe versus simulation. Because to truly grasp what it would mean to bend spacetime and outrun light, it is necessary to grapple with a question even more daunting than how to cross the stars. What, in the deepest possible sense, is this reality that would be crossed? Reality, as it appears, may be the greatest special effect the universe has ever pulled off. It feels immediate, direct, and unquestionable, a three-dimensional world of objects and places stitched together by the unbroken flow of time. Yet the closer science looks, the more this apparent solidity dissolves into something far more elusive: patterns, probabilities, and relations hovering behind the scenes. To understand what it might mean to bend spacetime and skip across light years, it is necessary to probe this deeper mystery. What kind of thing is the universe, really? One way to approach this question is to step back and look at the foundations of perception and measurement. Every experiment in physics, every observation made by a telescope or detector, ultimately terminates in a human or machine observer registering an outcome. A sensor clicks, a screen lights up, a number appears in a database. From these outcomes, theories are built and refined. But the raw event, the click of a detector, is not reality in its entirety. It is an interface point, a surface contact between a mind and a world. This may sound abstract, but the implications are immediate. If everything known about the universe is filtered through sensory and instrumental interfaces, then there is never direct access to things in themselves. What is possessed are model-structured descriptions that organize experience, make predictions, and allow technology to be built. The question becomes, do these models reveal what the world is, or only how it behaves relative to specific ways of probing it? Here, a major divide opens between competing views of reality. On one side stands scientific realism. Realists argue that the success of physics is not a coincidence. The reason theories work so well is because they describe, at least approximately, how the world is independent of observers. According to this view, electrons, fields, and space-time curvature are not just useful concepts. They are features of a mind-independent universe. When a physicist writes an equation, they are, in a very real sense, uncovering part of the cosmic blueprint. Realism is powerful and intuitive, and it aligns well with the engineering triumphs of modern science. Build a bridge using equations for stress and strain, and the bridge stands. Aim a probe using orbital mechanics, and it arrives at Saturn. Adjust for relativistic time dilation, and GPS satellites and navigation systems work. It is natural to think that such repeated success could only happen if the underlying theories capture structures that truly exist out there. On the other side stand more cautious or radical positions that challenge how far this inference can go. Some philosophers and physicists argue that theories are instruments, tools for organizing observations and making predictions, not windows into the ultimate nature of reality. This stance, sometimes called instrumentalism, treats entities like electrons and wave functions as calculational devices rather than literal pieces of the world. In this view, asking, "What is an electron really?" may be like asking, "What is a weather map really?" beyond its role in summarizing conditions. Between strict realism and pure instrumentalism lie nuanced positions. Structural realists, for example, suggest that what science truly captures is not the intrinsic nature of things, but the relational structure between them, patterns of interaction, symmetries, and invariances that remain stable even as theories change. According to this perspective, earlier models like Newtonian gravity were not entirely wrong. They approximated certain structural relationships that newer theories like general relativity refine and embed in a broader framework. Quantum mechanics complicates all of this dramatically. In classical physics, it was easy to imagine that objects have definite properties, positions, velocities, energies, whether measured or not. Experiments merely revealed what was already there, but quantum theory replaces definite states with superpositions, collapses, and probabilities. The wave function encodes potential outcomes, not pre-existing facts. A measurement does not simply uncover a value, it plays an active role in determining which possibility becomes actual. Different interpretations of quantum mechanics offer rival stories about what is real. The Copenhagen-style view is famously modest. The theory is about measurement outcomes and their probabilities, not about unseen realities between measurements. Many worlds interpretations propose that all possible outcomes occur in branching universes, with observers experiencing only one branch. Objective collapse models suggest that wave functions spontaneously localize under certain conditions, turning possibilities into single realities without needing observers. Bohmian mechanics introduces hidden variables, adding precise particle positions guided by an underlying wave. Each interpretation agrees on the same experimental predictions, but paints a radically different picture of what exists. Is there one universe or many? Are probabilities fundamental or emergent? Does the act of observation play a special role, or is it just another physical interaction? The lack of consensus reveals something crucial. The mathematical formalism of quantum mechanics is astonishingly successful, but its metaphysical meaning remains unsettled. Against this backdrop, another radical idea has gained attention: that information, not matter or energy, might be the most fundamental ingredient of reality. In an information-centric picture, what really exists is a web of bits or qubits, basic yes, no, or quantum states, and physical objects are higher-level manifestations of how that information is arranged and processed. Space, time, and particles would then arise as emergent patterns in a vast informational structure. This perspective gains support from how deeply information appears in modern physics. Black hole thermodynamics ties the entropy of a black hole to the area of its event horizon, suggesting that the amount of information it can contain scales with surface area, not volume. Quantum entanglement, the strange connection whereby two particles share linked properties even when separated, seems to encode correlations that transcend classical space. Some proposals for quantum gravity attempt to reconstruct spacetime itself from patterns of entanglement, as if geometry were woven from informational links. If information truly underlies everything, then reality becomes a kind of computation, a universe-sized process unfolding according to rules. This does not necessarily mean a literal computer built by someone, but it does make the idea of the universe as a simulation more concrete. If the basic substrate is informational, then in principle, the difference between a natural universe and a simulated one collapses. Both would be processes running on some underlying hardware, whether that hardware is physical, mathematical, or something even more abstract. The simulation hypothesis rides this line between metaphor and literal claim. It suggests that what is experienced as the physical universe might be the output of an immense calculation performed by some higher-level system. Observers, including humans, would then be subroutines within that computation. Physical laws would be the rules of the program. Quantum randomness might be algorithmic randomness. Spacetime itself could be the emergent stage of a deeper digital dance. There are reasons to be cautious about taking this literally. The hypothesis is difficult to test, and some arguments for it rely on speculative assumptions about the capabilities and motives of hypothetical simulators. Yet its popularity highlights a larger shift in thinking: the willingness to see the universe in terms of processing, encoding, and representation. Even if no external simulator exists, the language of information and computation may still be the right way to describe what reality is doing at its core. Running parallel to this are ideas about emergent spacetime. Certain theoretical frameworks, especially those grappling with quantum gravity, propose that spacetime is not fundamental but arises from an underlying network of relationships. Imagine a web of nodes connected by links, where each link encodes some quantum correlation or informational relation. At large scales, this web could look smooth and continuous, much like how a dense grid of dots can give the impression of a solid line from far away. Distance and direction would then be macroscopic illusions, emerging from microscopic patterns of connectivity. In such pictures, what it means to move from one place to another changes drastically. If space is a derived concept, then traversing it may amount to reconfiguring relations in the underlying network, rather than sliding objects through a pre-existing arena. Topology, the way nodes are connected, becomes more fundamental than geometry, the precise distances between them. Shortcuts that look impossible in ordinary space might correspond to simple rewiring in the deeper graph. This is where notions like wormholes and quantum teleportation enter the story. Wormholes in general relativity are hypothetical tunnels connecting distant regions of spacetime. Quantum teleportation is a process by which the state of a particle is transferred from one location to another using entanglement and classical communication, without moving the particle itself. Both are different manifestations of a single theme. Information and connectivity can reshape what distance means. Imagine a fabric with threads woven tightly together. At the macroscopic level, the cloth appears flat and uniform, but at the microscale, individual threads can be looped, knotted, or pulled together. Two distant points on the cloth surface might be adjacent in terms of thread connections. In an emergent spacetime, something similar could, in principle, occur. Two regions far apart in ordinary coordinates might be closely linked in the underlying structure. Creating or exploiting those links could enable almost instantaneous transitions that, from the emergent perspective, look like shortcuts through space. From this vantage, warp drives and other exotic faster-than-light schemes are not just engineering challenges. They are attempts to access and control the deeper connectivity of reality. Bending spacetime around a ship might be one macroscopic expression of a more profound operation, altering the pattern of relationships that define where and when events occur. To do this safely and reliably would require an intimate understanding of the layers beneath spacetime itself, the very layers that current physics is only beginning to map. All of this raises a haunting personal question. What then is a conscious observer within such a layered, possibly informational universe? If reality is a process, a structure, or even a simulation, then the human self is not a small, separate spectator watching the cosmic show. It is part of the show, a pattern sustained within the larger pattern. Neuroscience reinforces this view from another angle. The brain constructs a model of the world, filled with objects, colors, sounds, and a continuous sense of now. It also constructs a model of a self situated inside that world, a center of experience, decision, and memory. This self-model is updated constantly as new sensory data arrives and predictions are adjusted. The inner narrative, "I am here, experiencing this," emerges from this ongoing modeling process. If perception is an interface and the self is a model embedded in that interface, then the relationship between you and reality becomes more fluid. You are not a ghost lodged inside a machine, peering out at a fixed external realm. You are a dynamic pattern participating in how reality becomes manifest at your point of view. Your observations, decisions, and actions are not outside the universe's unfolding. They are part of it, just as a whirlpool is part of a river. This does not mean that reality is all in the mind. Quite the opposite. It suggests that mind and world are intertwined expressions of deeper structures. The universe gives rise to systems that can model it. Brains, instruments, civilizations, and those models, in turn, influence what happens next. The feedback loop between observers and the observed becomes part of the story of reality itself. Now, set this against the backdrop of interstellar travel and warp drives. If spacetime is emergent and malleable, if information is fundamental, and if observers are embedded patterns within this grand process, then the idea of going somewhere else becomes more subtle than it first appears. To travel to another star is to change the relational configuration connecting one localized pattern of experience to another. Faster than light travel, in this light, is not about violating a fixed speed limit in a fixed arena. It is about reprogramming the arena. The philosophical positions realism, anti-realism, information centrism, simulation ideas, emergent spacetime all offer different lenses on what such reprogramming would mean. A realist might say, we are learning deeper laws governing the real, external world and gaining the ability to manipulate its geometry. An instrumentalist might respond, we are refining our tools for predicting and controlling experiences, extending the range of possible observations. An information theorist would add, we are discovering new ways to route and transform information in the universal network. A simulation enthusiast could insist, we are accessing administrative privileges in the cosmic code. Whichever lens one prefers, the implications converge on a single point. Reality is not as rigid as it once seemed. The speed of light limit, once described as an absolute, begins to look like a constraint within a particular level of description. A rule that may be bent if access is gained to the deeper structures that generate spacetime itself. Warp bubbles, wormholes, and quantum connectivity are not just speculative tricks for science fiction. They are signposts pointing toward a universe where distance, time, and even objecthood are emergent phenomena, subject to revision under the right conditions. But this is not merely a cosmic engineering problem. It is also a question about meaning. If the universe is layered, if perception is an interface, and if the self is a dynamic model within that interface, then what does it truly mean to go to the stars? Is it about relocating matter from one region of spacetime to another? Or is it about expanding the range of experiences accessible to conscious patterns like experiences of alien skies, unfamiliar suns, and new forms of life? In the end, the quest to travel faster than light is inseparable from the quest to understand what light, space, and time actually are. The drive to break free from the gravitational well of Earth and the drive to penetrate the conceptual wells of everyday intuition are two expressions of the same impulse, a refusal to accept the first story reality tells and a determination to find the deeper narrative hidden beneath. As the story unfolds further, the focus turns more directly toward you, the conscious observer trapped in a human body on a small planet, in a vast universe that might be more fluid, more informational, and more open to transformation than any previous generation dared to imagine. Because if space-time can bend, if distance can be rewritten, and if the universe is, at its core, a dance of patterns and information, then your role in that dance may be far more profound than simply watching from the sidelines. You are not just an observer standing outside the story of the universe. You are a thread woven into its fabric, a localized knot of consciousness experiencing reality from one particular angle. Every thought you have, every decision you make, every sensation that arises in your awareness is an event within the larger unfolding of cosmic history. The question is no longer whether the universe exists independently of observers. It almost certainly does in some form, but rather, what role does observation, measurement, and conscious experience play in how reality manifests moment to moment? This is where the philosophy becomes personal, where abstract debates about realism and emergence connect directly to the experience of being alive and aware. If perception is an interface shaped by evolution, then what you experience as the world is a species-specific rendering optimized for survival, not necessarily for truth. Colors do not exist in the electromagnetic waves themselves. Sound is not carried in the air pressure fluctuations. These qualities are constructed by the brain as useful labels for navigating an environment filled with opportunities and dangers. The same applies to more fundamental aspects of experience. The sense of a continuous, three-dimensional space filled with persistent objects may be one way among many possible ways to organize sensory information. Other organisms, bats using echolocation, octopuses with distributed nervous systems, hypothetical alien intelligences might construct radically different experiential worlds from the same underlying physical substrate. Each interface would be tuned to the survival needs and sensory capabilities of that particular form of life. This raises a vertiginous possibility. If the experienced world is a user interface, and if different observers can have different interfaces, then there is no single view from nowhere that captures what the universe really looks like. Instead, there are multiple perspectives, each valid within its own frame of reference, each representing a slice through a deeper, more complex reality that no single vantage point can fully encompass. Reality becomes less like a photograph and more like a vast, multi-dimensional sculpture that looks different depending on where you stand and how you shine light on it. Now, apply this to the problem of interstellar travel. From the perspective of everyday human experience, the stars are distant points of light separated by unimaginable gulfs of empty space. To reach them requires crossing those gulfs, which in turn demands either immense time or speeds approaching the cosmic limit. But this framing assumes that the everyday interface three-dimensional Euclidean space with fixed distances is the only way to describe the problem. What if it is not? What if, at a deeper level, the universe is better described as a network of informational relationships, where distance is a derived concept rather than a fundamental one? In such a picture, two stars separated by light years in ordinary space might be connected by shorter paths in a deeper topology. Accessing those paths would not require moving through every intermediate point in the familiar three-dimensional grid. It would require changing the way the connections themselves are structured. This is essentially what warp drive proposals attempt to do, albeit described in the language of general relativity rather than information theory. By compressing space in front of a ship and expanding it behind, a warp bubble creates a shortcut not by moving faster through space, but by altering the geometry so that less space needs to be crossed. The destination comes closer while the ship remains stationary in its local frame. It is a hack, a way of rewriting the rules by exploiting the flexibility inherent in spacetime structure. But if spacetime itself is emergent, if it arises from deeper layers of quantum entanglement or informational connectivity, then warp drives might be only one of many possible shortcuts. Wormholes, another exotic prediction of general relativity, would represent even more dramatic topological transformations. Literal tunnels through spacetime connecting distant regions. Quantum entanglement hints at correlations that defy classical notions of locality, suggesting that information can be shared between particles instantaneously, regardless of separation. Each of these phenomena points toward a universe where the surface geometry is not the final word. The challenge, then, is not just engineering. It is epistemological. To build technologies that manipulate spacetime or exploit deeper layers of reality, it is first necessary to understand what those layers are and how they relate to the observable world. This is where the competing interpretations of quantum mechanics, the debates over information and emergence, and the philosophical questions about realism all converge on a practical concern. How can knowledge of the deeper structure be leveraged to achieve outcomes that seem impossible within the surface description? One way to think about this is through the concept of phase transitions. In physics, a phase transition occurs when a system shifts from one state to another, water freezing into ice, a magnet losing its magnetization above a certain temperature, a gas condensing into a liquid. At the macroscopic level, these transitions can look sudden and dramatic, even though they arise from smooth changes in the underlying microscopic conditions. Near the critical point of a phase transition, small perturbations can have large effects, and the system becomes highly sensitive to external influences. Spacetime itself might undergo something analogous to phase transitions under extreme conditions. Near black holes, the curvature becomes so intense that the familiar concepts of before and after, inside and outside start to break down. At the Planck scale, the absurdly tiny length scale, where quantum effects and gravitational effects become equally important, spacetime might cease to behave like a smooth continuum at all, instead revealing a foamy, discrete structure. Creating a warp bubble or opening a wormhole could be seen as inducing a controlled phase transition in spacetime, nudging it from one geometric configuration to another. If this is the right way to think about it, then the key to faster-than-light travel lies in understanding the conditions under which spacetime becomes flexible enough to reshape. This might involve extreme energy densities, exotic quantum states, or precise control over vacuum fluctuations. It might require materials or technologies that do not yet exist, but it also suggests a pathway forward, rather than brute, forcing through the cosmic speed limit. The goal is to coax spacetime into adopting a geometry where the limit no longer applies in the way it normally does. There is a parallel here with how human technology has historically overcome apparent limits. Flight seemed impossible because humans are too heavy to float and lack wings. But by understanding aerodynamics and building machines that exploit the principles of lift and thrust, flight became routine. Similarly, communication across oceans seemed limited by the speed of ships and the reach of shouting. But by discovering electromagnetic waves and building transmitters and receivers, instantaneous global communication became reality. In each case, the limit was overcome not by violating the underlying physics, but by accessing a deeper or broader aspect of it. Faster-than-light travel might follow the same pattern. The speed of light limit is absolute for objects moving through spacetime, but spacetime itself is not absolute. It is dynamic, curved, and possibly emergent. By learning to manipulate the deeper layers, the effective constraint can be bypassed without technically breaking the rule. It is the difference between trying to run faster and faster until you exceed a speed limit versus changing the road so that your destination is suddenly much closer. This brings the focus back to you, the conscious observer embedded in this flexible, layered universe. Your experience of distance, time, and separation is mediated by your brain's model of reality, a model built from sensory data, memory, and prediction. That model is remarkably stable and consistent, but it is not the territory itself. It is a map, and like all maps, it simplifies, distorts, and omits details. The question is, can you, through science and technology, extend or alter that map to encompass possibilities that currently lie outside your everyday experience? In a sense, every scientific instrument does this already. Telescopes extend vision across light years. Microscopes reveal worlds invisible to the naked eye. Particle accelerators probe scales far below what senses can detect. Each tool expands the interface, giving access to phenomena that would otherwise remain hidden. A warp drive, if it can be built, would represent another such expansion, a way of extending the range of accessible experiences to include destinations that are currently beyond reach within a human lifetime. But there is something deeper at stake. If consciousness itself is a pattern maintained within the informational structure of the universe, then your identity, your sense of being you, is tied to a particular configuration of matter and energy localized in space-time. To travel to another star, in the conventional sense, means transporting that configuration across vast distances. But if space-time is emergent and malleable, other possibilities arise. Could a sufficiently advanced technology reconstruct the pattern that is you at a distant location without moving the original atoms? This is the idea behind teleportation, not in the quantum sense of transferring states between particles, but in the science fiction sense of scanning, transmitting, and rebuilding a person. It raises profound questions about identity and continuity. If a perfect copy of you is created elsewhere and the original is destroyed, is the copy really you? Or is it a different person who merely shares your memories and personality? These questions are not idle speculation. They cut to the heart of what it means to be a conscious observer in a universe where the boundaries between self and world, between here and there, between now and then, may be more fluid than intuition suggests. If the self is a model constructed by the brain, and if that model can, in principle, be instantiated in different substrates or locations, then the persistence of you over time becomes a matter of informational continuity rather than physical continuity. Even without teleportation, long-duration space travel raises similar issues. If you board a starship and spend decades in suspended animation or traveling at relativistic speeds, you will emerge in a future where everyone you knew is gone, where culture has evolved beyond recognition, where your home world has become a memory preserved only in historical records. In a very real sense, you will have traveled not just through space, but through time, arriving in an era that is foreign to you. The you that arrives is separated from the you that departed by a gulf that is as much temporal and cultural as it is spatial. This is why faster-than-light travel is not merely a technical convenience. It is a way of preserving connection, continuity, and context. If the trip to Proxima Centauri takes days instead of decades, you can return to find your friends and family still alive, your civilization still recognizable. The interface, the experiential world you inhabit, remains coherent and continuous. You are not an exile jumping forward through history. You are a traveler exploring a larger space within the same historical moment. If you're enjoying this journey into the nature of reality, consider subscribing to our channel, Broken Zach, so you don't miss what comes next. But the deeper implication is this: if space-time can be reshaped, if distances can be compressed, and if the structure of reality is more flexible than everyday experience suggests, then the limitations you feel, the sense of being trapped in a single body, in a single location, in a single moment, may be less fundamental than they appear. They are features of the interface, not bugs in the underlying system, and interfaces can, in principle, be redesigned. This is where the philosophical and the personal merge. To contemplate faster than light travel is to contemplate a future where the human experience is no longer confined to a narrow band of accessible space and time. It is to imagine a species that has learned to navigate the deeper layers of reality, manipulating the very fabric of existence to expand the range of what is possible. And in doing so, it is to imagine a transformation not just of technology, but of consciousness itself, an evolution in how beings like you relate to the universe you inhabit. The journey from Earth to the stars is not just about building better rockets or discovering exotic physics. It is about extending the map of reality to include regions that currently seem unreachable. It is about learning to ride on the substrate of space-time itself, sculpting new geometries and opening new pathways. And ultimately, it is about recognizing that you are not separate from this process. You are part of the universe, learning to reshape itself, a conscious pattern within a vast informational web that is slowly, incrementally, beginning to understand its own structure. The next stage of the story turns toward the practical consequences of these ideas. If warp drives are possible, even in principle, what would it take to make them real? What obstacles remain, not just in energy and materials, but in the fundamental physics that govern whether such manipulations of space-time are truly allowed? And what might happen if humanity or some other intelligence elsewhere in the cosmos succeeds in crossing this threshold? Because if faster than light travel is achievable, then the universe becomes a very different place. The galaxy is no longer an unreachable tapestry of distant lights. It becomes a neighborhood filled with worlds that can be explored, contacted, and perhaps even colonized. And if one civilization can learn to bend space-time, others might have done so already, leaving behind traces and signals that are waiting to be found by those who know how to look. If warp drives are real, if space-time can truly be folded and manipulated, then the implications cascade outward far beyond the mechanics of propulsion. The universe transforms from a cold, empty prison into a navigable ocean. Distances that once seemed absolute dissolve into engineering challenges. And the question shifts from, can we ever leave? To what happens when we do? But before that threshold can be crossed, there are hard, unyielding obstacles that remain problems not of imagination, but of energy, materials, and the stubborn constraints written into the laws of physics themselves. The most immediate barrier is power. Even with Harold White's optimized warp bubble geometry, which reduced energy requirements from Jupiter mass equivalents down to hundreds of kilograms of exotic matter, the numbers remain staggering. Converting hundreds of kilograms of ordinary matter into the kind of negative energy density needed for a warp field would require power outputs comparable to stars. Current human civilization generates roughly 20 terawatts of continuous power, a pittance compared to what would be needed to sustain even a modest warp bubble for more than a fraction of a second. Nuclear fusion, the same process that powers the sun, offers one potential pathway. If controlled fusion becomes practical, and despite decades of research, it remains tantalizingly out of reach, it could provide energy densities far beyond anything chemical reactions can produce. A fusion reactor compact enough to fit on a spacecraft, but powerful enough to warp spacetime, would represent a leap in engineering comparable to going from candles to nuclear reactors. Yet even fusion may not be enough. The energy must not only be generated, it must be concentrated and shaped with extraordinary precision to produce the asymmetric space-time curvature a warp bubble requires. Antimatter represents the theoretical upper limit of energy density. When a particle of matter meets its antimatter counterpart, both annihilate completely, converting their entire mass into pure energy with perfect efficiency. A single kilogram of antimatter reacting with a kilogram of matter releases energy equivalent to dozens of thermonuclear bombs. The problem is production. Creating antimatter requires enormous particle accelerators, and current technology can only produce it one particle at a time. Accumulating even a gram would take thousands of years with present methods. Storing it safely, preventing it from touching any normal matter, and detonating adds another layer of nearly insurmountable difficulty. Even if energy and exotic matter can be obtained, there is the question of control. Generating a warp bubble is one thing. Steering it, stabilizing it, and ensuring it does not collapse catastrophically is another. The space-time geometry inside and around the bubble would be highly dynamic, with intense gravitational gradients at the boundary. Any instability could cause the bubble to implode, potentially releasing its stored energy in a violent burst. Passengers inside would need to be shielded from tidal forces that could stretch and compress matter at the molecular level. The engineering tolerances would make building a fusion reactor look simple by comparison. Then there is the problem of exotic matter itself. The Casimir effect demonstrates that negative energy density can exist in nature, at least in a relative sense, but scaling this from nanometer gaps between metal plates to meter-scale fields surrounding a spacecraft is an open question. Some physicists have proposed using metamaterials, artificially structured substances that manipulate electromagnetic fields in unusual ways to amplify Casimir-like effects. Others suggest that rapid oscillations in the vacuum energy, driven by intense laser pulses or other quantum techniques, might generate the necessary conditions temporarily. But all of these remain speculative. No one has yet demonstrated sustained, large-scale negative energy density in a laboratory. There is also a subtler concern rooted in quantum field theory. The energy conditions that govern what kinds of matter and energy are physically allowed place strict limits on how much negative energy can be concentrated in a given region and for how long. Violating these conditions too severely might trigger instabilities that prevent warp bubbles from forming in the first place, or cause them to evaporate almost immediately. Some researchers have proposed quantum inequalities that bound the amount and duration of negative energy, suggesting that nature has built-in safeguards against certain kinds of space-time manipulation. Whether warp drives fall inside or outside these bounds remains an active area of theoretical investigation. Assuming these obstacles can be overcome either through breakthroughs in physics or through technologies not yet imagined, what would a functioning warp drive actually look like? The ship itself might be surprisingly conventional. A metal hull, life support systems, perhaps rotating sections for artificial gravity. The exotic components would be external, a framework of field generators surrounding the vessel, creating and maintaining the bubble of warped spacetime. From the inside, the journey would be eerily smooth. No acceleration forces, no sense of motion, just a ship sitting still in its local patch of space while the universe slides past outside. To an outside observer, the ship would appear strange and distorted. Light from the vessel would be severely redshifted or blue-shifted, depending on the direction of observation, making it partially invisible or glowing with strange colors. The bubble itself might emit exotic radiation as it moved, leaving a detectable wake through space-time. This is important because if warp drives are possible, they might be detectable at a distance not just by seeing the ship, but by observing the gravitational waves or other signatures produced by the moving space-time distortion. This brings up one of the most tantalizing possibilities. If warp drives can be built, perhaps someone else in the galaxy has already built them. The universe is nearly 14 billion years old. Earth and its sun are relatively young compared to many other star systems. Intelligent civilizations could have arisen billions of years before humanity, giving them an immense head start in technological development. If even a small fraction of those civilizations discovered warp drive or similar space-time manipulation techniques, the galaxy could be crisscrossed with the traces of their journeys. Gravitational wave detectors like LIGO and Virgo have opened a new window on the universe, allowing scientists to observe ripples in space-time caused by colliding black holes and neutron stars. These instruments are sensitive enough to detect distortions in space-time at scales far smaller than an atomic nucleus, even when those distortions originate from events billions of light years away. If a warp drive passes through the galaxy, it would generate its own gravitational signature, a moving pattern of space-time curvature distinct from natural astrophysical sources. Searching gravitational wave data for anomalous signals that do not match known sources could, in principle, reveal evidence of advanced civilizations manipulating space-time. This is not science fiction. It is a legitimate research proposal that several physicists have explored in recent years. The challenge is distinguishing artificial signals from the noise and from natural sources, many of which are still poorly understood. But the possibility remains. Buried in the data already collected or waiting in future observations, there might be evidence that someone out there has already solved the problem humanity is only beginning to grapple with. If such evidence were found, it would be one of the most profound discoveries in human history. Not only would it confirm that faster-than-light travel is possible, it would prove that other intelligences exist and have reached a level of technology far beyond current human capabilities. The universe would suddenly feel much less empty and much more dangerous, because any civilization capable of bending space-time at will would possess power on a scale difficult to comprehend, power to traverse the galaxy, to manipulate energy on stellar scales, and perhaps to reshape planets or even solar systems according to their needs. This raises uncomfortable questions about why, if such civilizations exist, humanity has not encountered them already. This is the essence of the Fermi paradox. Given the age and size of the universe, intelligent life should be common, and at least some of it should have spread across the galaxy by now. Yet, the skies are silent. No radio signals, no mega structures, no unambiguous evidence of visitation. Where is everyone? One possibility is that faster-than-light travel is ultimately impossible, and all civilizations remain trapped within their home systems or limited to slow, generation-spanning voyages that make galactic colonization impractical. Another is that advanced civilizations exist but choose not to contact or interfere with younger species like humanity, either out of ethical restraint or because they operate on timescales and with motivations so alien that contact is simply irrelevant to them. A darker possibility is that there is a great filter, some insurmountable obstacle that prevents civilizations from reaching the stage where they can spread beyond their home worlds, whether through self-destruction, resource exhaustion, or some other catastrophic failure. If warp drives or similar technologies are achievable, the great filter might lie ahead rather than behind. Perhaps the technologies required to manipulate spacetime are also technologies that can easily destroy civilizations: antimatter weapons, runaway vacuum decay, or destabilization of spacetime itself. Perhaps learning to bend the fabric of reality comes with risks so severe that most species do not survive the transition. Or perhaps the universe has mechanisms, still unknown, that prevent or punish large-scale space-time manipulation, ensuring that the cosmic speed limit remains effectively enforced despite the theoretical loopholes. Alternatively, it is possible that warp-capable civilizations do exist, but remain undetectable because their activities look like natural astrophysical processes. A sufficiently advanced technology might be indistinguishable from background noise warp signatures lost in the chaos of supernovae, black hole mergers, and gamma-ray bursts. Or they might have moved beyond physical space-time entirely, uploading themselves into computational substrates or transitioning into forms of existence that do not require physical travel at all. But set these speculations aside for a moment and return to the human side of the equation. Suppose, against all odds, that the obstacles are overcome. Suppose humanity or its descendants develops a working warp drive within the next few centuries. What would that mean for the future of the species? The immediate consequence would be the opening of the galaxy. Thousands of potentially habitable worlds, currently unreachable, would become accessible within reasonable time spans. Voyages measured in years or decades instead of millennia. This would not just enable exploration. It would enable migration, colonization, and the establishment of a truly multi-world civilization. Humanity would no longer be confined to a single fragile planet vulnerable to asteroids, climate shifts, or self-inflicted catastrophes. It would become a distributed species, with populations on dozens or hundreds of worlds, ensuring survival even if individual planets failed. The cultural and psychological effects would be equally profound. The sense of isolation that has defined human existence since the dawn of consciousness would finally break. The stars would no longer be unreachable points of light, but destinations, places with their own landscapes, ecologies, and perhaps even inhabitants. The universe would feel smaller, more intimate, more knowable. The ancient human drive to explore, which carried ancestors out of Africa and across every continent and ocean, would find new frontiers on a scale almost unimaginable. But it would also bring challenges. Contact with alien life, if it exists, could range from enlightening to catastrophic. Even microbial life on other worlds could pose biological risks, introducing pathogens for which Earth organisms have no defenses. Intelligent alien species might have values, technologies, and agendas radically incompatible with human interests. The history of contact between human cultures with differing levels of technology is not encouraging. Faster-than-light travel would make such contact not just possible, but likely. There would also be economic and political upheaval. Access to the resources of other star systems, exotic materials, energy sources, even entire planets would shift the balance of power in unpredictable ways. Who controls warp drive technology? Who decides where humanity goes and how those new worlds are used? The geopolitical struggles of Earth could expand into a galactic arena, with conflicts playing out across light years. Or, more optimistically, the sheer scale and abundance of space might reduce competition, making cooperation more rational than conflict. On a deeper level, faster-than-light travel would force humanity to confront the nature of its own existence in new ways. If space-time is truly malleable, if distances and durations can be rewritten, then the framework within which human life has always been lived, a framework of here and there, now and then, self and other, begins to look less like an unchangeable given and more like one configuration among many. The boundaries that define individual identity, cultural continuity, and historical context would soften. What does it mean to be from Earth if you were born on a ship traveling between stars or in a colony world orbiting a sun 50 light-years away? And if warp technology can compress space, might it also, under certain conditions, manipulate time? General relativity links space and time inextricably. Any sufficiently exotic space-time geometry that permits faster-than-light travel might also, in principle, permit closed time-like curves paths through space-time that loop back on themselves, allowing travel into the past. This opens a Pandora's box of paradoxes and instabilities. Most physicists believe that nature has mechanisms to prevent true time travel, even if warp drives are possible. But the mere theoretical possibility is enough to suggest that mastering space-time manipulation could have consequences far stranger and more profound than simply enabling interstellar voyages. All of this assumes success. But there remains the very real possibility that, despite tantalizing hints and promising calculations, warp drives ultimately prove impossible. Perhaps the energy requirements, even with optimization, cannot be reduced to achievable levels. Perhaps exotic matter cannot be generated or stabilized at the scales needed. Perhaps there are quantum constraints that forbid sustained negative energy densities. Perhaps the universe, despite its apparent flexibility, has hard limits that cannot be circumvented no matter how clever the engineering. If that turns out to be the case, then humanity faces a different future, one of slow expansion, generation ships, and suspended animation, one in which the galaxy remains vast and mostly unreachable, and the dream of walking on alien shores under distant suns remains forever out of reach within a single human lifetime. It would be a universe that demands patience and continuity across centuries, where exploration is an endeavor not of individuals, but of entire lineages. Yet, even failure in this particular quest would not diminish the deeper insight gained along the way. The attempt to build a warp drive has already reshaped understanding of spacetime, quantum fields, and the relationship between observation and reality. It has pushed the boundaries of what is considered possible and revealed hidden structures within the laws of physics. Whether or not faster-than-light travel ever becomes real, the journey toward it has expanded the map of human knowledge and imagination in ways that will echo for generations. And that, perhaps, is the truest measure of progress. Not whether a specific goal is reached, but whether the pursuit of that goal opens new pathways, reveals new truths, and transforms how beings like you understand the universe and your place within it. If warp drives remain forever beyond reach, the universe stays what it has always been for us, a distant spectacle, breathtaking yet untouchable. But if even one of the pathways hinted at by modern physics is real, if space can be bent, if emergent spacetime can be engineered, if the informational architecture beneath reality can be accessed, then everything changes, not just for our technology, but for our understanding of what it means to exist at all. Because at the heart of this entire story lies a quiet but profound realization. The laws of physics are not just constraints. They are also invitations. They invite questions, experiments, and the discovery of loopholes, subtle ways of working with the grain of reality, rather than trying to bludgeon through it. The speed of light, once interpreted as a hard wall, begins to look more like a rule that applies within a particular layer of description, a rule that may be bent by stepping down into the deeper machinery that generates space-time in the first place. For you, as a conscious observer, this has implications far beyond the prospect of someday boarding a starship. It means that your sense of limitation, the feeling of being bound to one small world, one narrow sliver of time is, at least in part, a feature of the interface your mind uses to navigate reality. That interface has served your ancestors well. It kept them alive on the savannas, guided them across oceans, and enabled them to build cities, telescopes, and particle accelerators. But it was never designed for understanding quantum fields, emergent geometry, or warp bubbles. Extending that interface through science, technology, and reflection is how a species like ours inches closer to the deeper structure of the universe. Think about what has already been accomplished. A creature that once stared at the night sky with nothing but naked eyes has learned that those points of light are suns, that many of those suns have planets, and that some of those planets may be habitable. That same creature has uncovered equations that describe how mass and energy curve spacetime, how particles can exist in superpositions, how empty space seethes with quantum fluctuations. We have built devices that detect ripples in spacetime from collisions between black holes billions of light years away, and instruments that can read the spectral fingerprints of water and oxygen in alien atmospheres. All of that emerged from the same basic process: minds constructing models, testing them, refining them, and using them to pry open new doors. Faster than light travel, if it ever becomes real, will be another door of this kind. But even if it never does, the attempt to open it has already deepened the relationship between consciousness and cosmos. It has forced us to confront questions that reach far beyond engineering. What is space? What is time? What is information? What is an observer? What is real? These questions matter because they feed back into how you live your life right now, long before any warp ship is built. If perception is a user interface, then humility and curiosity become essential virtues. Humility, because the world you experience is not the whole story, and many of your intuitions are tuned for survival, not truth. Curiosity, because the interface can be extended. You can learn to think in ways that are not natural, but are more accurate ways that incorporate quantum strangeness, relativistic geometry, and the possibility that reality is layered, emergent, and more flexible than it appears. They also matter because they reshape your sense of meaning. In a universe where distances are vast and lifespans are short, it is easy to feel insignificant, a tiny spark flickering briefly in an indifferent void. But flip the perspective, and something remarkable appears. That same void has, through processes we are only beginning to understand, given rise to beings who can ask questions about it, map its structure, manipulate its laws, and imagine futures in which they roam its depths. You are not outside the universe looking in. You are one of the ways the universe looks at itself. If warp drives one day carry us to other stars, that will not be a story about machines alone. It'll be a story about a long chain of minds. From the first humans who followed animal tracks across unknown valleys, to the mathematicians who wrote down the equations of spacetime, to the engineers who learned to contain stars in magnetic bottles, to the crews who decide to risk everything on a journey into the dark. It will be the universe, through us, testing what is possible within its own rules. And if they never do, if the speed of light remains, in practice, an unbreakable boundary, then the story is still extraordinary. We will have learned that we live in a cosmos where some dreams are constrained not by a lack of imagination, but by the deep logic of reality itself. There is dignity in discovering the limits of the possible, just as there is wonder in discovering loopholes. Either way, we will have expanded the domain of human understanding, turning mystery into structure and structure into meaning. One day, perhaps, a distant descendant of ours will stand on the shore of an alien sea, under a sky pierced by constellations that do not exist from Earth. Maybe they will arrive in a ship cocooned in a warp bubble, having crossed light years in days. Maybe they will be the children of travelers who slept in the dark between the stars for centuries. Or maybe they will be digital minds, patterns of information transmitted across the galaxy and reassembled in new bodies beneath foreign suns. However they get there, they will look up at that alien sky and know that they are part of a story that began long before humanity and will continue long after. A story in which a universe learned, step by step, to understand and transform itself. A story in which beings like you played a role not as passive spectators, but as co-authors of what comes next. And you, sitting here now, wondering whether faster than light travel is a dream, a destiny, or a beautiful impossibility, are part of that unfolding. Your curiosity, your questions, your willingness to imagine a reality larger than the one handed to you by your senses, All of that is the first movement in a journey that may one day span the galaxy or may instead carve deeper understanding into a single world that remains our only home. The universe may or may not allow starships to outrun light, but it undeniably allows minds to outrun their own limits. That, in the end, is the real warp drive, not a ring of exotic matter around a spacecraft, but a ring of ideas around a small, fragile species, expanding outward faster and faster into the unknown. If you enjoyed this video, watch this one too. It's a great one, and we'll see you in the next video.